Okay, so today we shall start next chapter, steam power plant. The basic cycle we covered in Thermo 2. So we'll start the same and then we'll go in much more detail. So for this chapter, these slides are made from actually all these 3 books I used. I could have covered everything from here or from other power plants, but it's very much same things which we have covered in Eunice Angel book. So why not to use the same symbols, same overall strategy? So that's why I'm using majority from here, but also there are some part from these 2 books. So the basic cycle we all know very well. So let's go through those basic components and the overall cycle and every process which we already know. Here you see furnace in which fuel and air are entering, and it is giving us that energy which is required in the boiler. Here, these 2 terms, mass of the fuel, again, because of a different book, is using W for mass flow rate. CV is the calorific value or heating value of the fuel, right? CV. So mass of the fuel, which is burning, multiplied by the calorific value of that fuel. This is the energy which is transferred to the boiler. Only energy is transferred, mass is leaving. Mass is not transferred. So this heat energy goes to the boiler. So what is happening in the boiler? This liquid water entering, and we are getting steam or gaseous water, which runs a turbine. So from a turbine, we get shaft work, which goes into the generator, and that gives us the electrical energy. To complete the cycle, this H2O, which was used here, again, there was a heat transfer, work transfer, no mass transfer. So mass is still here. So this mass goes to the condenser. We want to repeat the cycle. So here the heat is rejected to whatever available sink. Okay. It's not always river or sea. It could be normal ambient air. Then to the pump where we have to supply work. And again, the cycle keeps on repeating itself. This is the basic steam power cycle. Because we have already covered, so I will not go into too much details of each of these processes. So if anything is not clear, then ask. Okay, everything is, I think, very much clear. Because I use this example from Thermo 1. I always use this example to explain everything. Okay, here you see, because this steam power plant is not just 4 components. There are so many other components which are providing us the required energy. So here we see a more detailed schematic, but still there are many components missing, but still some more detail compared to the previous cycle which we saw. So there are so many other components, so many auxiliaries and accessories which are required to achieve that task, right? Depending upon, of course, availability of water is a must. What type of fuel is available to us? So accordingly, you have to construct the plant. Fuel means coal. Then you have a different fuel handling system compared to coal or oil or gas. And of course, the service for which the plant is intended. What is the purpose of this plant? Okay, for how much megawatts? Okay, so accordingly, the choice of these components will change, right? Even if it's a nuclear power plant, only this part is different. The rest is same, exactly same. Okay. So here you see coal storage, coal handling plant, where we convert the coal into a form which is easily combustible, crushing it, cleaning it. So all these processes. So that itself is a complete chapter you can see in your PowerPoint book. So no, of course, to reach higher temperature, but coal is not available in pure form when you take it from the earth. So you have to purify it. Then you have to crush it. You have to make it a uniform mixture, which can be boiled easily. Okay, so on one side, that is coal handling, or if it is oil, then oil handling system. Oil refinery is there somewhere, which is giving us the required amount of fuel. The other thing is air. Okay. Either we use normal ambient air at normal temperature, or to increase the efficiency, we preheat this air so that you can get maximum out of this fuel. If air is already very cold, so much energy will be used up to just heat up that air. Okay. So we can preheat this air with what? With this exhaust gases. Now, exhaust gases are not only heating this air, they are heating some other components, which I will explain. And this is coming in later on in this chapter. Okay. So this spoiler is receiving air from this side and coal or fuel, whatever fuel, from the other side. So in that boiler, there is a combustion or furnace, which is not shown here. Boiler, we use the term where the water is evaporating. Only that part is actually called boiler. But normally we use the term boiler, including superheater. Superheating is not a pure boiling phenomenon. Boiling is only inside the dome. Before and after, it's actually not boiling. Okay. That single phase region. Okay, that's why here those regions have been separated. Here we see a term economizer and superheater. Those are representing those two regions. This region, this is only boiler. And this region is superheater. This region, subcooled region, here we use a separate component, which is called economizer. And you see here, this exhaust gases, they are, after combustion, those gases, they first go into superheater. So they transfer their energy to this fluid, which is at highest temperature. Superheater is this part. Okay. And then they go to the boiler. That is not shown here properly. We will see when we'll be discussing boiler separately, a separate chapter of boiler. So first, these combustion gases, they go into the superheater, then to the boiler, and then to the economizer here. Because here economizer, it is at the lowest temperature. So exhaust gases, after supplying their heat, flue gases to superheater and boiler, still their temperature is higher than this economizer. So this is the same flue gases which are used here first in the superheater, then in the economizer. Economizer is this part. Superheater is this part. And between superheater and economizer, it is boiler. It is going to the boiler, then to the economizer. Okay. So this schematic can be changed a bit. Okay. No, this is different thing. I told you. I explained what is this arrow. Okay. So anyways, this was the fuel. Here is a furnace which we can add. Then from that furnace, fluid first goes to the superheater, then to the boiler, then to the economizer, and then to the air preheater. Now the temperature is lowest, but still temperature is in hundreds. 3 or 400. It can be used to preheat this air which is entering at ambient temperature. So after combustion, these flue gases are used to perform so many tasks. 1, 2, 3, and this is the fourth one. And still the temperature will be high enough we can use it for any other purpose. We will see cogeneration plants where we can still use this heat. Not here in Bahrain, but in Western countries, they use this heat for space heating during winter. Space heating during winter. What is going on in this room? Space cooling. Space heating during winter if you need to heat the room. So that is what we will see in coming chapters. Okay, so things are very messy. So this is the part we just covered. Now, finally, it goes into the chimney. The parts which we can add here separately is furnace. Let's show furnace separately where the combustion is taking place. Okay, then here this sequence can be changed a bit because these highest temperature gases first goes to the superheater, then to the boiler, then to the economizer, then to the air preheater. Okay, so from the boiler, what we get then? Yeah, steam. Which steam? Here is the boiler. Here was the water entering, coming from the economizer, then to the boiler, then to the superheater. Where? Okay, he is showing flue gases here. Okay, steam is here, going to the superheater, right? Okay, steam he has shown here to the superheater. Now it goes towards the turbine, a valve which is open because here you are controlling the amount of steam flow rate according to whatever is the load requirement. Load is varying. If load is varying, so here is the valve. And not only this valve here, then you have to control. There is a control for combustion also. Here you also controlling these things. Airflow, fuel flow, steam flow, everything is. If you control this one, those are automatically controlled. So that is control. It should be like this. Otherwise, there should be a person controlling this. There should be a person controlling this separately. When this is closed, so this should automatically be closed when mass flow rate drops. Boiler. Fuel, yeah. According to the requirement of the generator. No. Yes, that could be one, or control this thing, because this is the steam which is producing power, not this one. So as you control this one, this will automatically send the signal to others. Okay, so here is the turbine, all right? Two chapters only for this part is coming, okay? And we know what happens. And then there is this whole system of rejecting heat. So it's not as simple as we show it just with a box. So here we have a condenser, a heat exchanger. In that heat exchanger, now it could be there is cold water flowing into that heat exchanger, and that cold water is rejecting its heat. In the cooling tower means to the ambient air, or if it's not a cooling tower, then there is whatever river or canal or sea water where it is rejected. So here is that heat rejection going on. So here the steam, which is to be reused. Okay, now here you see two more components which we never discussed before. This water which is coming out of the condenser, this liquid water, here you see low pressure heater. There is a pump which increases the pressure. Then you are heating it. How you are heating, I will tell you. Then there is another pump which increases the pressure more. There you have another heater. Then it goes into the economizer. So before entering the economizer, here you see two more heaters. That is what we will learn in this chapter. Okay, in coming chapters, before economizer. Yeah, this is what we will discuss. Let me show it briefly here. That is the fluid coming from the condenser. Now you heat it. You increase the pressure. Then you heat it. Then you again increase the pressure. Again heat it. Then again increase the pressure. Okay, dome is too short here. Okay, so there could be many reheating processes. Now, what is the source of this reheater? Yes, the steam, they take the steam at different pressures from the same turbine. Okay, so that is what we will see this part in this chapter later on. That will increase the overall efficiency. Why efficiency is so important? Because efficiency is the one which is telling us how much fuel we are consuming. So, okay, so for very large power plants, thousands of megawatts, we want this efficiency to be as high as possible so that we can conserve the fuel. Okay. So there are already two heaters, then it enters into the economizer, and then boiler, then superheater. Okay, so this part. So here you will see in the turbine section, there is reheating something going on, and this heat is transferred somewhere here. So these things we will discuss in coming slides. No, not for normal steam power plants, no. But there are some steam power plants in the world, but very few, which are operating in supercritical range. Right, for supercritical range, the material of construction should be very expensive so that they can sustain such high supercritical pressures and temperatures. Okay, so we'll see also, that will also come. So this is, and here is the, you see, ash handling plant, because there are certain amount of that fuel which does not combust. Yeah. So that has to be taken out. All right. So here, this is an overview of a steam power plant with more components shown. So the amount of piping is there, the amount of insulation which is used everywhere. Now you can just imagine. And normally this is one power plant. You make, for example, 30 megawatt of this multiple plants, or one big 1,000 megawatt, and so on. So, and everything, look, heat exchangers, heat exchanger, 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 heat exchanger. So many heat exchangers that it's all heat transfer. Heat transfer is so important. Without this, you cannot complete the design. Okay. All right. So let's start with the Carnot 1, which we already discussed in Thermo 2. If you learn Thermo 2 with me, then you very well know what we discussed. Recorded lectures are there, so I do not need to consume so much time here. Carnot heat cycle, 4 processes, 2 isentropic, pump and turbine, 2 heat transfer, 1 heat addition, other heat rejection. All are fully reversible. Then it will give us a rectangular shaped structure, and that we can show for a steam power plant inside the dome. That is possible. Outside the dome, this is impossible. You cannot have a constant temperature heat addition. You cannot have a constant temperature heat rejection. outside the dome. So inside the dome, it is possible. So we can show the steam power plant or vapor power cycle, another term for steam power plant. We never use the term vapor for gas power plant. Normally, we use the term vapor when we are in this region, near or inside the dome. Okay. So 4 main processes are clear. That is the only possibility to show those 4 processes of Carnot cycle for a steam power plant inside the dome on TS diagram. So, but what are the issues? This is not an issue. Yeah. So if you remember, this was the issue. The turbine is working inside a 2-phase region throughout. And the pump is also working in a 2-phase region. All right. So far, we have a pump which operates in the liquid region. Turbine, either it's all liquid hydro or all gas or steam. There is no turbine which operates in 2-phase region throughout, and there is no pump which operates in 2-phase region throughout. Okay. Why we discussed, I do not want to go into that. Erosion, cavitation, okay. So then therefore there is a need. So this is a Carnot cycle, but this is not practically feasible. So that's why we have to make certain changes. What are those changes? Shift this 0.3 T here and 0.4 to here. So what will happen? This 0.1, because this is one pressure, this is another pressure. So this 0.2 has to be shifted here so that 0.3 ends up here. And this 0.4 should be shifted here. So then 0.1 will also shift here. So 4 to 1 process, it's all in liquid, and 2 to 3 process, it's all in gaseous region. This is the turbine, steam turbine. This is pump. Okay. So Carnot cycle needs this modification, then it doesn't remain a Carnot cycle, because now during heat transfer, temperature is changing. During heat rejection, although we are at 3 to 4, but we shall see the in practical systems, you will not achieve exactly 0.3, right? Yes.
You have a good new material turbine pump that can handle the
2-phase region.
Isn't that wind has very little energy?
Look, energy, you are only watching this thing. Look, you have to see how much heat you are transferring. You're also transferring less heat. Region is small, so the heat transfer is also small. So the ratio becomes still higher. And here, if you remember, we used to discuss in thermo that everything is for 1 kilogram of mass. If you need higher power, increase the mass flow rate. But from 1 kilogram, this is the maximum efficiency we can. Okay, so the rest is already discussed. This is another possibility to operate a steam power plant like a Carnot cycle, but then look, 4 to 1 is in one region, 2 to 3 is in one single phase region, but now this is very difficult to achieve 1 to 2. You cannot have a constant temperature process above the dome. That's not possible. Temperature will increase. So whenever there is a heat transfer with the change in temperature, that is what irreversible. There will be changes on system sides around it, right? Okay. So that is also not possible. Okay. So that's why we have made changes in the Carnot cycle to make it more practical one. So that practical cycle is the one which we call as Rankine cycle, the basic Rankine cycle. Okay. So 1 to 2 is still ideal Rankine cycle. I will name it as ideal Rankine cycle. Why ideal? Because 1 to 2 is process is assumed isentropic. S1 is equal to S2. We are still assuming there is no friction. Similarly, 3 to 4 process is still assumed isentropic. So again, we are neglecting frictional losses. And also we are assuming this heat transfer process, there is no friction. It is a constant pressure process, but in actual real processes, pressure will drop during these heat transfer processes, 2 to 3 and 4 to 1, because fluid is flowing through pipes and there will be friction. So pressure will not be constant. So still, it is an ideal process. Not a corner, but still ideal, but more near to practical. Yep. So that has been discussed here. We already covered in Thermo 2. That's why naming, if you are still not sure what are the meaning of this one, don't sit in this class. Yeah. Go back and revise your basics if still you are not sure what this means. Yeah. Okay. So let's move on. Let's do the energy analysis. That is also we covered already. So energy analysis means apply energy balance for each control volume separately. Okay. Assuming 1 kilogram of fluid flow and apply steady flow energy equation to each of these components, boiler, turbine, condenser, pump, by neglecting kinetic, macroscopic kinetic and potential energies changes across these components. Okay. So starting from the boiler, so this will end up this thing. H3 minus H2 is equal to Qn. No work transfer for turbine. H3 minus H4 will give us work of turbine, assuming no heat transfer. For condenser, H4 minus H1. Okay, no work done during this process. This is called pump. This is pump, which we also call feed pump, which is feeding the water to the boiler. Here it is again H2 minus H1. And you already know how to find all those enthalpies. Except here the issue is for the pump. For the pump, which is entirely in the liquid region, this difference between 1 and 2 is only due to pressure. And these pressure lines are very, very close to each other in the liquid region. So for pump, and even if you can write it as U2 plus E2V2 minus U1 plus E1V1, that is enthalpy. So in the pump, this change in temperature is negligible. Change in temperature is negligible means this U2 minus U1 is negligible. So, and the change in volume, specific volume of a liquid, does it change? It's so here you can take it common V1, which is equal to Vf here into what is left, P2 minus V1. So for the pump, use this equation. Difficult to find enthalpies from table or chart. We'll see tables and charts. Charts, which we will see, those are readable here. Those are not readable here. Lines are so close to each other. Pressure lines, especially. So for the pump, we'll be using this equation. For others, the same enthalpies, which we calculate. Okay, so that is explained here. There is the work of pump, where H1 is nearly equal to HF and V is V1, which is equal to Vf. at that pressure P1. Okay, let's move. Efficiency clear. Network means, yeah, and that can be shown like this if you apply overall energy balance. So that can be shown that W net is equal to Q in minus Q out. So replace it here. So this is another way to write the efficiency. Okay. Or W net Q in minus Q out is equal to W turbine minus. So the same, all those processes are shown on TS diagram, and area under the curve on TS diagram represents energy. Yes, energy, but which energy? Area under any curve on TS diagram represents heat energy. And area under any curve on PV diagram, work energy. Look here, you have work. 3 to 4 is work, but area under this curve is 0. But it doesn't mean energy is 0. Heat energy, we are saying it's 0. Okay. Area under this curve is also almost 0. So this 2 to 3 area under this curve 2 to 3 is representing Q in, and area under this curve 4 to 1 is representing Q out. And we know from the overall energy balance, Q in minus Q out is actually representing net work output. So this area is our net work output on TS diagram. Okay. So this should be as high as possible, and this should be as low as possible. This heat transfer Qn. This should be as low as possible. This should be as high as possible. Okay, so that's what we will cover in coming slides. All right, so that is clear. Yeah. Okay. Yeah, everything is clear. Let's move on. There is another term which is used in the analysis of this steam power cycle, specific steam consumption, SSC. This is what we never discussed before. SSC is the steam flow required to develop the unit power output. So steam flow required to develop unit power output. M dot, what is the power output? It's 3 minus H4 is the power output of the turbine, only turbine I'm saying, not net power, only turbine power. In any case, this is negligible. So power input of a pump compared to turbine work. That is named as SSC. This is kilograms per second of steam, same kilograms per second of steam. That will cancel. So it is 1 over kilojoules per kilogram, or kilogram of steam required to produce this much kilojoules. That is so amount of steam which is required to produce 1 kilojoule of work. Or if you do not like in this unit, so let's write in some other units. For example, do not cancel it. Let's name it kilograms per second. Keep it in kilograms per second. So then this is kilowatt. Okay, let's convert this second into hours. So then this term can be written as kilogram per kilowatt hour. Right. So this term is actually also representing this thing, and this is normally used. How much kilogram of steam is required to produce 1 kilowatt hour? So the same term is also representing this thing. Because normally people are using watts, kilowatts. No one communicates in joules or kilojoules, right? So this term m dot over m dot into delta H of turbine is actually telling us the amount of steam to produce 1 kilowatt hour for that particular power plant. Okay. So you can also quote this thing, or this is one thing on the basis of which you can compare the different power plants. One company is saying our power plant, steam power plant, require this much steam to produce 1 kilowatt hour. Another one is saying, no, our consumes less due to whatever reasons, right? Yeah, another way to to highlight efficiency. Okay. Clear? Okay. Here, important thing. Look here. What is this thing? So it means it is network, but he is only considering turbine work because this is negligible. Okay. But if it is not negligible, then it should be H3 minus H4 minus H1 minus H2. Okay. So yes, so I was saying turbine work. No, it is network because here you see this symbol, and it should be network. Okay. Okay. Now let's discuss this thing. We have a separate chapter of boiler, but briefly let's see what is happening inside a boiler. So the term boiler is normally used for the overall heating process, but specifically boiler is only the part which is inside the dome. But normally after this fluid which is entering into this section which we are calling as boiler, it has three functions. First, to increase the temperature of liquid water, then to evaporate that water at a constant temperature, and then to superheat. So here you see furnace, flue gases. First they come in, because here the temperature is highest. So they come in contact first with the superheater, then the boiler, then the economizer. So that process. So area under this curve is representing economizer. Area under this curve is representing evaporator or boiler. But we use the term boiler overall for this entire process. So here, that's why we are calling it evaporator, if I want to say boiler for this whole thing. And area under this curve is representing superheating. Okay. Yeah, this is the only thing which we want to. And on the basis of that, we can also define ratio. Area under this whole curve from here till here, let me name it 1, 2, 3, 4. So the fraction of heat which goes into the evaporator can be written as H1 minus H2 minus H1 divided by H4 minus H1. That is the fraction of heat which is going to the evaporator. This is, economizer. Area under this curve is this thing divided by the total. Fraction going to the evaporator. Similarly, fraction going to the evaporator, economizer, evaporator, superheater. And the maximum will be this area. Here I've shown it like this. Maybe it's like this. This area is not that big in the single phase region. Latent heat is highest. Okay. Now here, same process is shown on TS, PV, and here is another HS. HS chart. Because in this course, I would want you to use this chart to save your time. Save your time means no need to see the tables, do interpolation. Directly use this chart because you have already learned how to use that table, how to do interpolation. No need to do interpolation in this course. Just use this table, this chart, HS chart. So we'll see that chart. Let's see if you can understand the processes. Here he has shown this boiling process from 4 to 1. On TS is clear. 4S means he's assuming isentropic before 4 to 1. It's clear on TS. 4 to 1 constant pressure process on PV. So this is 4 to 5. Temperature is in because these are temperature lines on PV diagram. So 5 to 6 inside the dome, 6 to 1. Same thing here on HS chart. On HS chart, these are pressure lines, P1 pressure, which is equal to P4, P1 to P4 on one single line. This is pressure line on HS diagram. So it is starting from liquid, ending here in the superheated region. Here is this dome. Dome shape is different because now X and Y axis are different, H versus S. So if you can show these 4 points on HS chart, directly read value of enthalpy from here, from this chart. Temperature lines are inside the dome, pressure and temperature are same. Outside the dome, this is temperature lines. These are temperature lines. Constant temperature lines. Okay, let me show this HS chart separately. This is clear. What is economizer, evaporator, superheater, and fractions, which is supplied in those. Okay, so this problem, which we already solved, this simple problem in Thermo 2, to find out the efficiency, you can calculate all those enthalpies. Let me show you this chart. This is the tables. Here you see 2 different versions of HS chart. HS. And of course, this is the dome, this red color. And these red colors, thin red colors are showing different. This is X is equal to 1. This is X is equal to 0.95. These are quality lines. This curve you can use only for superheated and for mixture region. This region is very difficult to read because those pressure, all these blue lines are pressure lines. They are converging to each other in the liquid region. So the same curve is shown separately here. Here you can see the liquid region, but it's not possible to read. So this chart you can use only for these 2 regions. For liquid region, you still have to use tables. Okay, because the same 2 charts you will be using in nozzles. In nozzles, you are here all the time. In turbines, you are again here. So for next 2 chapters after gas turbine, nozzles and turbines, it's better to use this chart directly. Okay. But now you need to understand that chart. Let's see different lines. Red line is clear. Same is here, this one. If you can find a better chart than this one online, share it with me so that we can print it. Okay. Because here, this is blue lines are pressure lines. On this chart, these pressure lines, their unit is bar. 0.01 bar, 0.05, 0.2 bar, 0.5 bars. So all these are in bars. These are pressure lines. Okay. Where are temperature lines? Do you see temperature lines? These ones, this one, for example. This is 500 degrees Celsius temperature line. So these are temperature lines. Inside the dome, this temperature and pressure lines merge, just like on TS or TV. So these are temperature lines, and here are the temperature values written. And what are these horizontal lines? Enthalpy. And what are these lines? Entropy. So you can directly read entropy or enthalpy from this chart. Just locate the point and read it. Yeah. If the pressure is between these two, just imagine where it is for this course, for exam only. Because later on in the industry, you have apps now. You have app. Just put pressure and temperature. It will directly give you all the properties. But here, as a student, you need to know what this pressure and temperature means, in which region you are. Same is here. Here the units are megapascal. Here the pressure units are megapascal. Okay. What else? One important term is missing here. So we have enthalpy, entropy, temperature, pressure, volume. Volume lines are not shown. If we show volume lines here too, then it's very difficult to read. So volume lines are very much similar to pressure lines. Slope is a little steeper. So there will be so many volume lines here. So you can see in Senjal's book at the end, there is HS chart with volume lines also. But on one A4 size page, it's not possible to read with the naked eye, or everyone brings that magnifier with him to read volume lines, okay? Or the values of volume lines. Or that's why if you can find a chart, which we can print on a bigger page, and even volume lines can easily be visible, okay, that's good. So this is the HS chart which we can use in this course. So now let's go back, because still there will be some challenges, because if your pressure is very small, like in kilopascals, here you have bars and here you have megapascals. So still it will be a bit challenge to trace that point. But that will be acceptable for this course, because I do not want you to waste time on the tables. Better to use this chart. So a slight error is acceptable. Okay. Now let's see this question. Quickly, this is the simplest question which we can have in this chapter, ideal Rankine cycle. So simply ideal Rankine cycle on TS diagram. Ideal Rankine. (75 kilopascal). 3 megapascal. This point is 350, 1, 2, 3, 4. Find out its efficiency. Efficiency 1 minus or W net over Q in. What is Q in? H3 minus H2. Q out. H4 minus H1. H1 is equal to HF 75 kilopascal. H2 H1 plus V into P2 minus P1. H1 plus V. What is V? V1. And V1 is equal to Vf at 75 kilopascal. So kilopascal multiplied by meter cubes per kilogram. That will be the units of volume multiplied by kilopascal. It should be kilojoules per kilogram. So check it. Thermo one. Kilonewton per meter square. I will not tell. Okay. H3 from HS chart at 350 and 3 megapascal. Let's see in that chart. 350 and 3 megapascal. Can we trace it easily or not? Three megapascal, 350. Here is megapascal. This chart is giving us directly megapascal or convert it into bar. 1 bar is equal to 10 to the power 5 pascals. Okay. How much was 3 megapascal? So here is 10 megapascal. Here is 0.1 megapascal. Here we have 0. Here is 2 megapascal. 2 and 5. 2 is written here. So here is 2. This is 5. Between them, 2.5 here somewhere. 3 megapascal. 350. Here is 350. So where is that? 350. And this is 3 megapascal. Three 100 or 3120. Because this is 3, this one is 3150 because this is 3200. So 3120, it's okay. For exam, it's okay. Yes, of course. You have apps, there are computer softwares, everything. No issue. So let's see what is H3. Okay, here is H3 from the tables. 3116, the exact value. So we will be saying 3120, 3110. It's okay. If you are saying no, I will calculate the correct one. Okay. Nobody is stopping you. But time will be same for everyone. Okay. So use HS chart. Okay. Because I will not allow MATLAB and laptops. You have to do it the conventional way. Okay. So therefore, better to use HS chart.
That's where charts were developed for designing the ones like actually they designed for.
Yeah. Even this whole power plant is we have softwares to build the whole power plant. Choose the boiler, put it here. Choose the turbine, connect it. Okay, that is not an issue. But before your theory is clear or not, what you are doing, you should know now exactly the physics behind. Okay. So that's how you, and you already know how to calculate H3. Now H4, you can locate this point 4 on HS chart. It may be inside the dome or outside the dome if you know this pressure and this entropy. So you need to locate 75 kilopascal pressure line, and point 3 is already located. Draw a vertical line. And wherever this 75 kilopascal line is intersecting this vertical line, this is your point 4. Okay. So HS chart is easy and directly read the value. Otherwise, waste time here. It's up to you. No need to waste time here because this is the simplest question. Do not expect this will come in the exam. Of course, the questions will be much bigger, okay, as we move in this chapter. Okay, so now we have discussed the ideal cycle, actual cycle. You will have pressure entropy change in the pumping process. It will not be isentropic. Entropy will increase because there is heat generation. Whenever there is heat generation, entropy will increase. Wherever there is heat rejection by the fluid, entropy will drop. Okay. So here, if we say heat is generated and transferred to the fluid. So entropy will increase. So this is pumping. Similarly, when the fluid is flowing through the boiler piping, the pressure will be dropping. So this point 3 will not end up here, somewhere here. Because it's to reach the same temperature, now you have to supply maybe more heat. 10, 3 to 4, non-isentropic, and then 4 to 1, again pressure drops in the condenser, pressure drop in the boiler, irreversibility in the turbine, irreversibility in the pump. So these pressure drops, if we neglect the effect of pressure drops, and you do not want to neglect this one, then what we used to do? Yes, efficiency term, or the ones who studied refrigeration, air conditioning, they also know we are using here isentropic efficiency formula to find out the actual one. Okay. So what are the sources of this irreversibilities? It's all, you know. Okay. So overall, the effect is your pump has to consume more work and you will be getting less work. So to get the same amount of work, you have to burn more fuel. In other words, because of these irreversibilities, efficiency drops. Okay, this is clear. This is not that difficult. We already discussed. So here we can define these two efficiencies to account for this non-isentropic processes. Actual process is now 1 to 2A, not 1 to 2S. And here we can define an isentropic efficiency of a pump, isentropic efficiency of a turbine. For a pump, ideal over actual or actual over ideal. In the pump, we supply work. What is the ideal pump where we have to supply less work or more work? Ideal pump means you have to supply less work. Less work is in isentropic or in actual process. That's why you see isentropic divided by actual. But in the case of turbine, it will be reverse. Because in the turbine, we need more work, and more work we will get in the isentropic. So for the turbine, it is isentropic divided by actual. Here for, actual over isentropic. Here, isentropic over actual. Pump or compressor, same. Okay. So we'll use this formula if we want to find out this actual point, 4A and 2A, but using isentropic. Less work. Who is he? In turbine, actual is less. Actual is less, isentropic is more. Okay. So these are the isentropic efficiencies. Okay. Here in this question, these isentropic efficiencies of pump and isentropic efficiency of turbine, both are given. And here actual conditions at every point is given. At the inlet of pump, at the exit of pump. Okay. Then, so of course in the pump temperature, pressure rises, temperature remains constant. If he has given some temperature, so then okay, but otherwise we will assume. But look here, from 2 to 3, in the piping, there is a heat loss. There is a heat loss, there is also a pressure loss. So from point 2 to point 3, pressure is dropped from 16 to 15.9, and temperature is dropped from 38 to 35. So between pump and boiler, there is some change which we have to take into account. Within the boiler, normally for ideal boiler, we say pressure remains constant, but here is showing pressure is dropped a bit. Here is the temperature which is given. Then from 4 to 5, you see another pressure drop and temperature drop. There is insulation, but still some heat is flowing through the ambient. So here, some actual data from a power plant is given. So using this actual data, temperature, pressure data, which is given here, and isentropic efficiencies of pump and turbine are given, we need to find out these thermal efficiency and the power output. So here the purpose is to practice an actual situation, not always ideal. Okay, this is what we shall do in the tutorial class today. This question. Here the challenge is to find out properties using table or chart. Okay. Yes.
So, what's the public efficiency is given by the manufacturer in the chart.
This is usually your good turbine should not have more than 15% of losses. It should be in this range. You cannot eliminate totally, but for a normal good turbine or pump, this isentropic efficiency should be between 10 to 20%. That's how you claim. And then once you make it, you check it experimentally. If there are more, why more? We need to.
How much?
When the fluid is flowing over such a surface, can I calculate friction loss? From fluid mechanics, Darcy's equation. Okay, if this friction loss is more, okay, do something with this surface. Maybe surface is very rough, or maybe the fluid flow is too high. It is giving too much friction losses. Maybe reduce the flow rate. So you see that equation, which is responsible friction loss for friction loss, FLV square over 2GD, work on it. Velocity, diameter, G. There is also this factor F has many parameters which are affecting Reynolds number, roughness. So work on it. Okay, so I stop here and we shall continue. We'll do only this problem in the tutorial class today.